Yeah, yeah. I changed the resolution to match what the projector wants. But it's all right. I mean, I'll go back and forth depending on. He's got to get feel for the room and everything.
Okay.
I got.
Do you want the lights on or off?
Uh, Lights off is a cool feel.
We're just going to introduce you, right? And then
Alright.
you start whenever you're ready.
Alrighty. Let me make sure. Check. Nope. Plugged in. Let me make sure that the microphone is able to move and.
So do you want the portable one? So you get
Yes,
the
yes,
whiteboard?
yes,
So you
please.
have the whiteboard as well.
Yeah. Oh, I'll be walking. Yeah, yeah.
You should use this one.
Okay, let me just make sure that it's.
Free now.
Let me run it over that. Yeah. Alrighty. That's enough. Yeah, Britney Spears probably couldn't be able to do with this, but I could. So. Yeah. Oh, I think I have a water ready just in case.
Yeah, yeah. So, welcome back from the coffee break. We will now have a presentation by Chris Rakakis. He's a research affiliate and co-principal investigator of the Julia Lab at the Massachusetts Institute of Technology, director of modeling and simulation at Julia Computing, and creator, lead developer of JuliaSeam. Director of Scientific Research at Pumas AI, and creator, lead developer of Pumas, lead developer of Scientific Machine Learning open source software organization. So, go on.
Alrighty. So today I see a very, very diverse audience in terms of backgrounds, in terms of some people who have been here a few times and they're like, oh, I've seen one version of your talk. There will be some new things for you, but for other folks, if you're like, oh, I don't even know what machine learning is, isn't that thing that NVIDIA is trying to make a bunch of money off of and is going to take over the world with robots, right? It doesn't matter who you are. There will be a part of this presentation that is for you. The point of this talk is really to try to find out exactly this problem right here. How do we make machine learning robust for scientific modeling, right? Because, okay, at this time point, raise your hand if you've used ChatGPT or some AI thing of some form. Everyone should raise their hand because when I say some AI thing of some form, I'm also including when you do a Google search, right? When you do a Google search, you type in, what is the most interesting thing in, and then it auto-completes with the word Azores in there before you've even written it down, right? That is a machine learning algorithm that you're using every single day. And you're using these algorithms every single day. And you understand that they work quite well, but then sometimes you type into Reddit, or sometimes you type in into Google something that's like, oh, the the coolest thing in, and and then Google auto completes with, I don't know, the bottom of my pants, and you're like, why did it do that, right? And there are errors that machine learning is doing all the time. And so what we're really looking at is, machine learning is some really cool tool. It's really kind of taking over the world. It's being used everywhere, but we see it make a lot of mistakes, and we can't make these mistakes in science, right? It's kind of funny when ChatGPT says something silly, but it's not really funny if 2 + 2 = 5 means that we're now making wrong predictions in a climate model, right? So what do we do about machine learning? What is it? How do we make use of it effectively in the context of science is really the question at hand here. And what we want to say is, okay, let's think about this as machine learning is our hammer. So, I just typed into Google, give me a weird hammer, and Google, never disappoints. If you find a Reddit thread right here that says, what kind of weird hammer is this, right? That's exactly the thought process that we should have with this, right? Machine learning and AI, it is a hammer. It is a tool. What kind of tool is it? That's the first question I want to address. Let's figure out what it is. So I'll start by saying machine learning is a thing for learning functions. Well, what do I mean by that? So let me take you step by step, right? So assume you want to find a function, right? You want to be able to put a number in here. You say, for example, give me your height, and I will predict what your weight is, right? That's a function, right? That's a function that exists out there in the world. There's a lot of people that are out there. A lot of people have a height, and you have a weight. And you probably think that, okay, the taller somebody is, the more likely you are to weigh more, right? And so what you might assume is that it's just the simplest relationship ever, right? Back in your 8th grade or whatever grade school that you learned this in, you say, okay, let me fit a line through my data. A line is the simplest thing. If you double your height, you maybe double your weight. And so if A = 2, this would be that relationship. We're basically just saying now we have the simplest relationship between height and weight. And you can turn this into a model. You can say, okay, if I have data points, I want to learn what is the best relationship between there, right? And now there's a whole science, and you'll find this in statistics, which is how to find the best version of A and the best B given data. But we're going to ignore all that for now. We're just going to, at a high level, we're basically choosing a model, right? What you do is you choose a model. You say, I want height to be related to weight, and I want to relate the two. And I'm going to assume that it's this kind of linear model, and I find the parameters of this model that make it so that way when you give me a height, I predict your weight, and I do it relatively well. It's never going to be perfect. That's too simple of a model, but we have a general idea. And you go, well, what if I need a better model? Because linear is a very strong approximation. It means if I double this, I know exactly how much is going to change. What if I need something more intense? You can start to say, well, let me start to maybe there's a curve in my prediction, right? Sometimes it could go down and sometimes it could go up. So for example, if you think about something like the predicted amount of rainfall in the Açores, right? And we think, what is given the temperature of yesterday? Well, there's a certain point where if the temperature was too high, maybe you increase the cloud cover, and so the cloud cover actually might cause less precipitation in tomorrow, right? And so there's not necessarily a relationship where things, if you increase the temperature, you always get more rainfall. There might be something a bit more complicated in there. And if you have a slightly more complicated function, like a quadratic function, you can catch more complicated things. And you can go, well, okay, if you can make things, if you can use x, your input, and you can use x squared, well, what about x cubed? What about x to the 4? Let me try everything. Let me try literally every single combination of these functions. And turns out mathematically you can do that, right? You can go, okay, I can have a cubic function. I can do actually all polynomials, right? Because what you can find within the mathematics is that, there's a Taylor approximation where any sufficiently nice function can be written out as a polynomial. So you can start to say, okay, let me use x to the 3rd power, 4th power, 5th power, and no matter what function exists within reality, I can find a way to be able to represent it through parameters. Now, okay, if you're a mathematician, you might be able to say that, okay, there are functions that cannot be represented by a Taylor series expansion, but that doesn't exist in Tessera. Right here, everything is nice, everything is beautiful. All realistic simple functions can be represented through a parameterized way, right? And so this is a way of being able to think of, okay, this is a process then for learning the world. I'm going to assume that any function that I'm going to try to approximate with data is some polynomial. I'm going to write that polynomial out far enough so that way it's just a complex enough polynomial. And then all I have to do is I need to find the numbers in there, right? I just need to find the numbers. What is A? What is B? What is C? What is D? And if I find these numbers, now I have some kind of complex object that fits the data well enough, and now I can predict. If you give me the height, I can give you the weight, predicted weight of the individual. And now the first thing that should be coming to your mind with this example, though, is you can just go, whoa, predicting height from weight, I mean, aren't you missing a few things, right? Because, okay, there is a relationship that the taller somebody is, the more that I'd expect them to weigh, but there's also other factors at play. For example, what are other predictive variables of this? Well, how many times that that someone actually goes out to eat and eat a steak? That's probably a predictor of of something to do with weight. Whether they have other medical issues, yada yada yada. Right? There's so many other things to predict. So maybe just having one input to be able to predict what someone's weight is not enough. Instead, you want to have many different inputs to be able to predict your output. Right? And this is the change where we start to say, well, we can represent every possible function that has one input, but what do we do if we want to represent every possible function that has 2 inputs, or 3 inputs, or 4 inputs? And then you can start to say, well, I can just do the same thing. I can make there be a line. This is what's now a multilinear function for every single input. I have one slope, a weight, by which if I increase someone's height, then I increase my prediction the number of weight. If I increase the amount of times you eat in a day, I might increase my predicted weight for you. And yada, yada, yada. Now I can have many variables that are part of this predictor, right? This is now a function which takes in many different inputs and outputs one output, right? And so this is where we get to with statistics, right? The statistical methods make use of this multilinear regression, which is a simple function of many inputs to predict how an output will work, right? So how do we go from this to machine learning? Well, I think the other way to ask is this: what is the core problem with this thought process, right? Well, let's walk through this. So in our first example, we said, oh, linear is too easy, right? We want to have very complicated functions. We want to learn complicated functions. So we can't just use linear. We need to make it go quadratic. We need to make it go cubic. We need to have more complex functions. Now, what happens if we have more than one input? Right? If we have one input, we say, oh, this is the linear version that has many inputs, right? Now, what is the quadratic version of that? Well, you can write in, the quadratic version is that you have to say, oh, I have, the combination of x1 with x1, the combination of x1 with x2, right? You could just write out all possible terms, and you put more weights. You put a weight on every single piece that goes in there. And this will give you a multi-quadratic function. And you never learned about this one in statistics, but you can come up with the mathematics to find out what are the optimal points for these predictors inside of for a given piece of data. And now you'll have a quadratic function that is for your predictor for all your inputs. Now, why do you not do this in practice? Well, if you think about it, right, the question really then becomes, how many terms do I have? So if I have n things, and I want to have every combination of 2 of them, how many terms do I have? Because I have x1 with itself, I have x1 with x2, x1 with x3, all the way to xn. They have x2 with itself, right? You have to count the number of things. And this turns into a permutation problem. It's the same thing as counting the number of permutations, which ends up being this weird thing of k plus n, choose n, minus 1. So that's the number of terms in a quadratic function. That will mean nothing to you because most people will not remember how to do the choose function. But now let's actually see what happens though, right? So if I was to say, oh, I have 100 predictors, and I want to write a cubic function in all of them because that should be complex enough. How many variables do I need to have inside of my function in order to write that down, right? And so what we could say is like, okay, if as long as you allow for a polynomial in all of your variables in every direction with all the combinations, we can mathematically represent every possible function. So why not just write, okay, this is quadratic. Let's make it cubic in all functions. Let's make it quartic in all functions. This will cover possibly everything, right? And so let's say you have one of these functions where n, this input here, is 100 things. And I just want everything to be a potentially cubic function. That's all I want. I don't need anything else. So how big of a computer do I need to represent that function? Well, I showed you the formula, so let's just type this into Wolfram Alpha, and it says if I have 100 inputs, if I have 100 predictors, and I want to have a cubic function on all of them, you would need 176,950 parameters. Right? The issue here is that the number of the number of things individually is growing with n, right? But the number of combinations between things that you have to look at grows exponentially. That's what you're finding inside this choice function. And so any extra complexity inside your function, if you want to represent it as a polynomial, requires exponentially more parameters of this polynomial in order to get any of that complexity in. And so this is the core problem where you just go, well, if I want to represent, if I have 1,000 predictors for how rainfall in the Azores will happen, right? I now have satellite images which give me, every single pixel of the image is one predictor. I have 100,000 predictors. This number will grow exponentially with the number of inputs, and so suddenly you need something larger than the largest supercomputer just to represent the number of weights inside your function. So this idea of, everything is just all polynomials, it works very well in statistics until you get to this point where you have lots and lots of predictors. So what can you do? Are we just done here? This is the end? No, the answer to this is neural networks, right? So you can think about neural networks, machine learning, all this pizzazz that everyone's selling to you. It is actually just one thing. It is a function representation. It is a choice of a function that is able to represent all possible functions. And it looks like this. Right there. Isn't that beautiful? This is the new meaning of life according to, Silicon Valley. What's really going on here is what you do is you do a linear operation, you do something nonlinear, you do a linear operation, and it turns out that if you make this linear operation large enough, it's able to represent all possible functions. So let me actually write down what this looks like a little bit, right? Just so that we're all on the same page, right? So let's say we have a function f of x1 and x2. Right? Now, a neural network is this black box that you call in some library that implemented it, yada, yada, yada. Okay, what's the library actually doing, right? What we do is we put our numbers into a vector here, x1 and x2. And we multiply it by a matrix. This matrix has a bunch of weights. So we might have, weight 1, weight 2, weight 3, weight 4, weight 5, and weight 6, right? And we do a matrix multiplication right here. Actually, this is no one called me out for missizing this. It means y'all aren't paying attention. All right, this is well sized. Let's see, yeah. Right, because if you do a matrix multiplication between these two objects, right, then you have w1 times x1 plus w2 times x2. You have w3 times x1 plus w4 times x2, and you have w5 times x1 plus w6 times x2, right? So that's your first operation, a matrix times a vector, and then you plus b1, b2, right? And now that's what the representation here. Now the sigma 1, what you do is you do some kind of nonlinear operation. So for example, sigma could be the function that is this, it could be the sigmoid function, or another common one is it's the tan h function. Just, one of these functions, your sine functions and your cosine functions, these weird things from mathematics, you stick one of these right here. So you take everything that you've gotten here, and now you just say, okay, I'm going to apply, I now have this vector, which is, let me rewrite it. So w1 times x1 plus w2 times x2 plus b1, and I'm going to take, tan h of that, the inverse tangent. And I'm going to not write down all of them, but I'm basically going to have 3 of these. And this is my new vector, right? Now I'm going to multiply it by another vector of weights. I'm going to say this is w7, w8, and now I'm going to write the w9, w10, and w11. Or actually, let me just do this with that size, right? When I multiply it like this, basically what I get out is I get W7 times the first row plus W8 times the second row plus W9 times the last row, right? This is one number. This is one number. Now if you think about this, there's a few different, but here's what happened, right? What are these W's? What are these weights? Well, these are the weights that you can choose in order to make sure that you match your data. So you can choose W to be anything you want. You can choose B to be anything you want. We fix this function, and what we do is we ask the question, what are the right W's? So that way when I put in a number, I end up getting the correct number out. Right? And there's a process, and that's called neural network training, which is to find the weights such that this function does something correct, right? Now, the purpose for choosing, this is a choice of a function, right? This is a procedure from going to inputs to outputs, which has a fixed number of weights. And the reason for choosing this form is because there's a universal approximation theorem, which states that, well, here's what I could have done, right? So notice I had 3 rows here. If I made this be n rows, if I made this be 5 rows, then I would have 5 rows here. And then all I need to do is I'd need to have 5 columns here. And I would still get one number in the end, right? So there's a choice here that I have, a choice which is the number, it's called the number of hidden layers, and it's just the number of rows that I'm choosing here. There's a theorem that says, as long as you make the number of rows of this part long enough, then this procedure for representing functions can represent all possible functions with 2 inputs to 1 output. And you can generalize this so that way for any function of n inputs to m outputs, this procedure, as long as you choose your weight vector to be large enough, can approximate every single possible function. And not only can it do that, it does that without having the exponential growth in the number of parameters. So that is the universal approximation theorem, and this is why we use neural networks. So in your mind, neural networks are this crazy, make robots, jump in circles and everything. But this is what it really is. This is behind the black box. It is just a procedure for taking in inputs to outputs that has a choice of weights, and there's a way to be able to choose these weights so that way you can represent every possible function in high dimensional spaces. So that's a neural network. When I ask, what is this weird hammer that we have that everyone wants? That is what it is. It is a device for approximating functions with high dimensionals of inputs that is able to do so with very few weights, in some way of saying very few. Yeah? Yes, there is a proof of this. So, I mean, for the mathematical proof, you have to say, for sufficiently nice functions. So, okay, for functions that are continuously differentiable, then there exists a size of the weights such that for all inputs inside of a fixed domain, the output that is predicted for some optimal choice of the weights is within epsilon for any delta choice, right? So there's an epsilon delta convergence proof that is showing that this is in some sense truly able to approximate every function, epsilon close, where if you choose how close you want to approximate it, I can give you the number of weights for this, right? And so, yeah, that's called the universal approximation theorem. There's many different forms of it, but basically it says that if you make your neural network big enough, you're guaranteed to be able to have it capture any amount of complexity. Now, then there's a lot of choices where, okay, how do you actually make that practical? How do you choose the layer size and such? That's instead just a process called graduate student descent, right, where your graduate student tries a bunch of choices to see, oh, this neural network is big enough, right? The theorems that tell you that you can approximate every possible function does not tell you how big the neural network has to be. It just says that there is a bigness to it that will work. Yep. Mm-hmm. There are some work that is doing that. Okay, so to understand what neural network size you should have, there is not good theory on it. There is something called neural network scaling laws, right? So neural network scaling laws. And what you find is that people from Google and such have realized that actually this is not the right plot. It took me a while to find the right plot, but basically people have been able to find that as we're training these larger and larger neural networks in tons and tons of different cases, we're finding that we can kind of predict like, oh, if you have 100,000 predictors, then you might want 10 million weights. And so there seems to be some natural scaling law in there that's being found empirically. There are not good mathematical proofs as to that right now. Yeah, let me see if I can. Yeah, all these things are just way too in the details in terms of the plots. But, I mean, there is this kind of general thing that people are finding across many different domains to be able to understand and predict what size neural network will work. But right now we say that this is something, you just have to find it out. But there is a size for which it will work out. That is at least the thing that you know. Yep. Yeah, well, so that's a funny thing, right? That's a funny thing, right? So why did I say tan h, right? Why did I say the hyperbolic tangent? It's because it's a function that is monotonically increasing, and that is one of the pieces that's required in the proof. It turns out that you actually don't need that to have a universal approximation theorem, but if you most of the proofs are done on very specific functions and such. And then there's a whole mathematical kind of part of the study, which is just trying to generalize, like, oh, you don't need that property. You don't need that property. What we're basically finding in the machine learning field is that anything that's nonlinear works. So you can have, for example, the ReLU function, right? The ReLU function, which is so if the ReLU function is 0 if x is less than or equal to 0, and x if x is greater than 0, right? This function is sufficiently nonlinear such that if you put it in for that sigma, you still get a universal approximator. It comes out as a Weierstrass approximation theorem proof, right? Yeah, so I mean, a lot of the proofs. I mean, there's kind of like as a field is evolving, you always kind of need to what is known and what do we know from practice, right? What we know from the theory of machine learning is that you do know that a large enough neural network is going to work, right? And you know that in a pretty general sense, a lot of functions, specifically ones that are monotonically increasing, will have this universal approximation property, right? In practice, what you know is these kind of neural scaling laws. People go, oh, in this case, this size neural network worked out well. This size neural network worked out well. And you know that some of the things required in the proof, like monotonic, are not really required in practice to make the machine learning work. And then you had to take that from there. But this is our hammer. Anyone have any other questions on this? All right. So this is our hammer. And now let's do science with it, right? So what we want to do is, we're going to say, okay, if we want to do robust science with this form of machine learning, what we want to do is we don't want to throw out our science. So what is science, right? What is our science? Well, a lot of our science is captured in scientific laws and theorems, right? So, for example, we have these models. We have, for example, if I was to ask you how the planets go around the sun, you'd immediately say, oh, you use Newtonian's law of gravity, right? We know Newtonian's law of gravity. Every high schooler is taught how to make predictions using Newton's law of gravity. So we have all these equations and these theorems and all this information, right? But now what we have is we have something that can find functions, right? What this other hammer can do is if you give it data, it can find a function that you did not know. So how do we put these two things together, right? Because in some sense, what we want to do is we want to be able to say data and our prior knowledge about how science works are both sources of knowledge. And if we can pool the two together, hopefully, using some of our prior scientific knowledge could be augmented with our new data knowledge to be able to make better predictions than either one alone. So this is the central hypothesis of scientific machine learning, that both sources of knowledge, Newton's law of gravity and measurements of the positions of planets, are both pieces of information, and let's use the two of those together to make better predictions than either one on its own. So the way that we're going to do this is we're going to start to develop scientific models, which are models that incorporate the prior knowledge that we have, the prior equations, but also incorporate this idea of I can learn functions on the fly. So let me show you how to do this through a step-by-step process. Right? what we're going to do is we're going to say, well, what is a neural network for? A neural network is something that can represent functions that I don't know. So what if I was to try to write down a mathematical model where I say, oh, so let's say this is the Lock-Voltaire equation, so x prime, so the change in the number of rabbits grows exponentially if I just have rabbits around, then I end up just getting more rabbits, right? They just kind of grow exponentially. And if I have wolves, and I just lock a bunch of wolves into a room, I get exponential decay in the number of wolves I have because they're just all eating each other, right? But now, if I put rabbits and wolves together in the same room, something happens. I don't know what happens. My mother never told me what happens if you put a bunny in the same room as a wolf, but but there is something that happens, right? And so this is what a neural network is able to represent. There is a function that goes here, and I don't know what that function is, so I'm going to write down neural network is all possible functions, right? So this is now my mathematical model. I know how to mathematically model this. I write it down. I know how to mathematically model this. I write it down. And I don't know what to do over here. And so I'm going to write down an object that represents all possible functions. And now how do I learn what function goes there? Learning what function I don't know is then equivalent to just finding the weights of this process. So I think that the best way to kind of explore this is to show this in a step-by-step example. So this example is looking at the start of the pandemic with data from the Wuhan region of China at the start of the COVID-19 pandemic, right? And what we're saying is, okay, can I predict how the pandemic is going to progress, right? The first thing I'm going to do here is say my predictor is just what's known as a neural ODE. It's U prime equals a neural network. So it's another way of saying this is U prime equals any possible function. So I have learn any possible ODE that fits the data. And what I'm going to do is I'm going to train it from day 0 to 21. I'm going to train it to be able to match the data, and then going to let it predict what the future is going to be like. And so this is what I did. I say, find a neural network that fits the data, and oh, hey, look, it's going through the data. It looks very good, right? And then I ask the question of, okay, once this neural network has learned a real function, now make a prediction of how the pandemic is going to progress in the future. And these lines down here are the predictions, and this is what happened with the real pandemic. Ooh, machine learning didn't do well, right? And so this is where a lot of people just pause and say, this is because machine learning does not know how to extrapolate, right? Which is a very high-level kind of hand-wavy phrase of, I know machine learning isn't able to do these problems quite well, so I'm going to give up, right? But let's actually think about it a little bit deeper, given this introduction, right? What a neural network is it's a representation of all possible functions. I told it, hey, learn a possible function from this data. And it did. It learned a possible function that fits this data. It just happened to be this line. This line is not really the function that predicts how the pandemic is expressing, but it is one that is true for these data points down here, right? And so the real issue that's going on here is that I'm asking it, hey, learn from the space of all possible functions, fit this data, and now it's not able to do a pandemic. But think about it. We know a lot more about a pandemic. The way that a pandemic should grow is not anything can possibly happen, right? Could the number of people who are infected in a pandemic be a negative number? That doesn't make sense. So, okay, we shouldn't really be letting it say, oh, let it learn any possible function. We should instead constrain this based off our scientific knowledge, right? Instead, we should say something like, well, I know that this is a pandemic, so learn any possible function, but the number of people who are infected should be a positive number. There shouldn't be -5 people that are infected on day 6, right? Okay, so I want to constrain that. But the other thing I know about a pandemic is if it's going to take off, there should be a peak, right? There's always a peak in every pandemic, so there should be a peak somewhere. And no one disappears in a pandemic, right? They're either always susceptible to the disease, they're infected, or they're recovered, or they've died. So I need to have that everyone always falls into one of these bins. I don't have my population just wildly changing every single day. There's nothing about the prediction of every possible function does not assume that these things are true. So how can we make it so that way things that we already scientifically know must happen are part of our learning process, and how much better can we make in our predictions if we force the function to be matching properties we already know to be true? And so this is where you get to this universal differential equation approach, right? So here what I'm showing is an encoding of a lot of the scientific knowledge through the form of a mathematical model, right? So if you haven't seen these SEIR type models, they were all over during the pandemic because they're a basic way to kind of capture a lot of the problems in the pandemic, right? So here S stands for the number of people who are susceptible to disease, right? And so people who are susceptible become exposed. People who are exposed to the disease, they get infected. People who are infected, they either recover or they turn into this D, where D is we don't talk about it, right? So what happens here? So when we write down this kind of mathematical model, we have to come up with a lot of intuition, right? So we have to say, well, the number of people who recover over time is some percentage of the people who are infected each day. So some percentage of the people who are infected, each day they turned into the recovered group. Now there's another percentage that turns into the D group, right? And we can go to the hospitals and we can find out, like, okay, how many people recover versus how many people die. We can find a lot of information about this mathematical model. And so we can get something that is relatively close. But when you start to write down a lot of these mathematical models, there's always a point where you're making an assumption. In this model, in the SEIR model, the assumption is, how do you make a function that is representing the rate at which people go from susceptible to exposed? That's a huge assumption, right? Because if you're in Boston in the United States, you had a lot of people who were staying indoors and during the pandemic, and so the rate at which people were becoming exposed to the disease was rather low. But in other parts of the United States, you suddenly had a Trump rally where people were running around and they all threw their masks off because it was suddenly like a sign of freedom. And so they had a completely different exposure function. And now if I'm trying to tell you, write down one mathematical function that covers how China works, how Sweden works, how different parts of the United States work, there's no way that you're going to write down a simple mathematical model, right? So instead I say, I have no idea what goes there. That's my neural network. And so this is one of these mathematical models then where I'm saying, I've written down a structure, a mathematical model where here's everything I know how to represent, but there are things that, I don't know how to represent this. So let me just put it there as I don't know, right? It's a representation of I don't know. And what happens when we do this? Well, what we do then is we use the data that we have on hand to train the neural networks to be these pieces of the model that we don't know. And when we do this, what we get is something that's able to make much better predictions, right? So again, here's our original model where we said, just learn whatever function from the data points and extrapolate into the future. It's not even close. Then we say, let's write down most of a pandemic model, but we don't know some things about our pandemic model. Let's just learn the things that we didn't know within the mathematical model. And what it's able to do is with the same 21 days worth of data, it's able to get almost 20 days of predictions quite accurate, right? And so basically what we're saying is we've infused the machine learning process with our knowledge of how pandemics work, and now we're no longer letting it learn every possible function. We're letting it learn functions that are representative of pandemics that also fit our data, and when you put those two pieces together, now it's a much better predictor of how the pandemic will work. It makes sense at a high level. Now, okay, there's a lot of hand waving there. Let me go back to the mathematicians in the room here. It's not just, I have infused the information of a pandemic into my mathematical process. It's a hand wavy glory, like the yada, yada, yada. Let me describe this now at a deeper level, what we have done, right? What we've done is we said, this entire thing right here, a mathematical model, is an approximator for how functions work. So instead of letting the machine learning be able to learn any possible function, I'm letting it learn any possible function right here, which is then constraining the type of possible function that can come out of here. So what are the types of possible functions that it can have that is this predictor? Well, if I'm taking the absolute value of the neural network, so if I take the absolute value of this thing right here, well, if you actually look at the formula of the differential equation, you actually have that S prime is negative. So in this model, I'm making the assumption that the number of susceptible people is always decreasing. And if you have that the number of susceptible people is always decreasing, then you actually can prove in this ODE form that there's actually a peak in E. So there's a peak in the number of people who are exposed, and then there's also a peak in the number of people who are infected. And also you have that from this ODE form, since you have minus the neural network and plus the neural network here, you always have that S plus E plus I plus R plus D is equal to a constant. So you have the constant number of people in this model. So let me take a step back here. What this is actually done, in one sense of the world, in a high-level sense, I have said I have infused my machine learning with epidemic modeling, and therefore it makes a better prediction of epidemics, right? In a deeper representation of this, I'm saying, I'm saying by using a mathematical model, now I have a universal approximator that has the following properties. Find me the function that predicts the number of people infected, where the number of people who are susceptible to disease is always decreasing in the start of the pandemic, where the number of people who are exposed will have a peak, where the number of people who are infected will have a peak, and the number of people who in this model always has to be constant. Right? These are, by writing this into the mathematical model form, I've implicitly made all of those assumptions, and what it does effectively is it has found a function that matches those assumptions and then makes a prediction. And it just so happens that that function ends up having a higher probability of being something that is realistically a predictor, right? And you can actually see that's leveling off. This model is guaranteed to always have a peak, right? And so the way to kind of understand what we've done here in a kind of high-level form is the following. What I'm truly saying is, let's say this is the space of all functions, right? So this is the space of all predictive functions. So this is the space of all functions, right? So if I want to make a prediction, if I want to make a prediction with machine learning, what standard machine learning will do is it'll just pick a function at random out of all the possible functions that fit. Well, let me split this apart. This is all functions, and in this section of it is all functions that fit your data. Right? And what machine learning will do is it will turn the neural network's weights into a function that fits your data. And it'll just pull one random function out of there and says, oh, this is a good predictor of, this is the best that we know how to do. Right? But it's not the best we know how to do. Right? Now let's split this again. This is all functions all F that fit data and have a peak number of infections. Right, because we know that a pandemic has a peak number of infections, so we should make this assumption that our functions should have that property, right? And then, all functions that have peak number of infections and have a constant number of people. All functions that have this and this and this and this. And now we're saying, all the way down here, now let's pick random. There's still a lot of functions that the machine learning can find, but let's pick randomly from this group. Right? And the assumption here is that if the true function really does match our scientific assumptions, then pulling a function randomly with all these correct assumptions should get you, on average, closer to the real one, and therefore be able to make better predictions on average. Right? And so that's hopefully a less hand-wavy way to be able to explain why the scientific machine learning should work. But this then shows you, this is in the result you tend to get, right? That your standard machine learning is just pulling a random function, and you say, oh, it didn't extrapolate well, I need more data, I need more this, I need more this. But if you actually then encode all the scientific knowledge into the way that you're doing the learning process, it's suddenly able to be a lot more predictive. And now the final step here is to say, okay, now that we have mathematical models, let me actually turn this back into a representation of a mathematical model, right? Because a neural network is just a function. So you can then ask it, what kind of function is this actually representing? And so you can turn this back into simple forms like a polynomial. So here what I did is I ran a sparse regression process to be able to get this function, and I could put it back into the equation. There's two interesting things that happen when you do this process. One is that it can decrease the number of predictor variables. So in this model, I allowed for the amount of exposure to COVID-19 to be a function of the number of people who are susceptible, infected, and who have died. And in the way that the neural network has learned how to predict exposure, it has given me this function. Can anyone see something interesting about that function in terms of those three variables? Do you see D in that function at all? Yeah, D is not in that function, right? Because I let this neural network be a function of S, I, and D, but it learned to be a function of S and I, and well, a normalized version of S. But basically, what this means then is that you can use your neural network as a tool to say, hey, be all possible functions and learn what goes here. And then when you start to look into the neural network, right, there are certain tools which are in the same organization, yada, yada, yada. But then you can turn it down into a simplified form. And what you might find is that, oh, the neural network is actually predicting that that people become susceptible to disease. The only thing that you need to know is how many people are susceptible and how many people are infected. That is a hypothesis given from the model that dead people are not infecting people with COVID-19. It's a reasonable hypothesis. I did not encode that by default. This is something that was discovered through finding this additional piece of the model, right? So we find this piece, but we also find that when we do the sparsification, we're able to improve the generalization from the model, right? This is still not a perfect predictor, right? It's still drifting. But again, for the same 21 days worth of data, I now have found a mathematical model through an automated process that is much better able to predict the trajectory of the pandemic. And by putting it down to this sparsified form, it has corrected for a lot of the behaviors of the neural network that happens when you're far out of that training data. I don't want to get too much into that part, but that's a detail there. So this is then this full process of the scientific machine learning, right? You start with a partial scientific model. You train a neural network to capture the pieces of the model that you did not know how to write down, and then you use the neural network to learn what functions you didn't know how to model in the first place. And now you have a corrected version of your scientific model that you can then use to make your predictions. And for a lot of different reasons, we find that this is a useful technique, not just for making better models, but for also improving the way that you come up with scientific hypotheses. And so then we put everything here into a nice, pretty picture, and this is what we put online. But I feel like, my running around and sweating a little bit with the whiteboard probably did it more justice than one little picture. And so next thing, so that's the general idea. But now let's get into this in a little bit, right? So we kind of had this idea that, okay, I could pour in model knowledge, and now you can understand, what is pouring in model knowledge? It's using more of my prior scientific information, my prior equations that I already know about. I can put those there, and I can augment it with data to come up with better predictive scientific models, right? But this picture is kind of a continuum, right? Now, and if you think about it, if I pour in more model, I should be able to pour in less data, right? Now, is that actually the truth? So a lot of what we did throughout 2020 and 2021 and 2022 was really this empirical kind of study and some analyses and such to be able to show that that truly is the case, right? Because let me take one step back here. At a concrete level, what I'm saying is, well, I put a neural network here because I didn't know what to do about the term for exposure, right? But I assumed that this term was true. I assumed that this term was true. I assumed, the neural network could have been capturing more of the model, right? So I could have had a bigger neural network and less model, or I could have had less neural network and more model, right? Like there's this trade-off between them. And what happens when you make that trade-off is really captured by a cartoon. It really is just this statement of, if you have less model that you've poured in, then you need to pour in less data. And we've been able to make that be a very concrete term. I mean, here's the actual papers if you want to kind of go back and see, the 30 pages of all da-da-da-da. No one really wants to read that, but the real detail is what we're able to do is we're able to do comparative studies across different epidemic cases to be able to show that the more model that we had, the more prior model that we had incorporated, the less data that was required to make the same prediction. Right? So if we want to have a certain prediction accuracy, the more prior scientific knowledge that you have, the less data that you need in order to make that prediction. It sounds super obvious. It is super obvious that, yes, if you know more about what's going on, then you don't need as much data to predict it, right? But this is the scientific validation that, this idea really does work out in terms of the mathematical form. And so you can take this cartoon and you can understand it. And so we're then able to start going, on and on and on. This kind of took off as a phenomenon. And so I know that folks here do a lot with weather prediction and such. So here, for example, is a blog post that someone named Sebastian Kala created using our tooling to be able to show that if you do this process in weather prediction using properties like mean temperature, humidity, wind speed, yada yada yada, then you can get a very good predictive model for weather, right? So saying, oh, this isn't just about pandemics. This is about weather modeling. This is about all sorts of different types of scientific phenomena. Right. Actually, my favorite case here that was an early validation of this approach is a quite nice one to understand. It might look tricky at first, but let me explain it in the human terms. Right. In the science terms, you have this. in the human terms, you have that Newton created the laws of gravity somewhere in the 1600s. It's a very simple law that says, okay, there's an inverse square law between that for how much gravity you have for a given planet, right? It turns out that he was not quite right. You know, Newton wasn't quite right, and so when things get really, really, really big, you have to have relativistic corrections, right? Can we actually, you know, and this took Albert Einstein to find it, so could we instead, you know, turn our MacBook Pro into baby Einstein and figure out how relativistic corrections work with just a small amount of data, right? And so this is effectively what this group did. They said, okay, we have two black holes that are orbiting each other, and we assume Newtonian mechanics. This is, you might not have seen it like this, but this is Newtonian mechanics in a rotating frame because black holes are rotating. So what you do is you just say, okay, I assume I know Newtonian physics, and I add these terms right here. What are these terms? These are the neural networks, F1, F2, F3, F4. These are just the outputs of the neural network. And you just say, I'm going to take Newtonian mechanics, I'm going to let there be corrections to it. What should learn what these corrections are, and for the black hole dynamics, and I should be able to do this. And they did this using the LIGO black hole data, and they're able to find that here the black points are the data points that they trained on. So just this small amount of data was used to be able to do the training, and from that they're able to learn how the dynamics of the system changed, and they're able to extrapolate out. The blue line is the true waveform, and the orange line is the predicted waveform. If they look like they're on top of each other, it's not just because the projector is a low resolution. They are actually close enough to each other to be about 3 to 4 digits of accuracy correct, right? Which in physics, we know things like 10 digits of accuracy, but I think most people will be totally fine if you got a 3-digit accuracy prediction, right? And this is just a different application of that same idea, right? There's some model that you know. I know Newtonian mechanics. I have some data, learn what the corrections are. In this case, it happens to be general relativistic prediction, but you know, in the same way, you have this in many, many, many different phenomena. Now, if you want more of these different validations, I would say there's a different talk that I gave before called Accurate and Efficient Physics-Informed Learning Through Differentiable Simulation. Check out this talk on YouTube. It goes into 20 of these different validation cases that shows, oh, here's how they were used in biology. Here's how it was used in chemistry. Here's how it was used in yada, yada, yada. I think they were at about 900 different scientific domains that have demonstrated that this approach is able to give you more accurate and predictive models, right? So I want to kind of go into the next point here. So if you follow me to here to be able to say, oh, I'm with you. I believe that this technique gives you more valid scientific models. I want to then go to the next point, which will be more interesting ways to use the basic technique. And I saw that there's a hand back here. Yeah. Yeah. Yeah, so for example, if we look back at the epidemic case, right? Like, here's like an intermediate type of model, SEIRD type model, right? It's a simple set of 6 differential equations, which is and then I'm using a neural network to capture an exposure, right? There are some simpler models, like just the SIR. I have people who are susceptible, infected, and recovered. I don't worry about how people are exposed and all those little. Like, there's a simpler version of this model. There's also a more complex version of the model, right? Where you actually build like an agent-based model. It looks like The Sims, right? And you have a bunch of people talking to each other, and they go, okay, if they're talking to each other and they're infected, then they might infect each other, and and you can build out an entire like virtual world, right? And what we've been able to find is that as you go to a more and more complex model with more and more accuracy, then you can use less data in the neural networks to predict the missing parts to be able to make the same predictions. Then if you have a much simpler model, then you need a lot more data for your neural network to give you something accurate, right? So it's this model complexity, right? If you pour in more prior knowledge, more model complexity, more scientific knowledge, then you need to correct for less of it with the neural network. I mean, it should be rather intuitive, but it is something that you do need to rigorously show in order to be able to make that statement in a general sense. More accuracy, yeah. Because there is a difference. Just because your model is more complex doesn't mean it's more accurate. So more correct accuracy, right? Because like here's the point that I'm really trying to make, right? That the process of learning, of machine learning, is about pulling a random point out of a function space, right? A neural network, when it has found its weights, you basically have found a random function that fits your data, right? So it's some random function that fits your data. And what you're trying to do here is you're trying to constrict the space to not be all random functions, but all random functions that satisfy x, that satisfy y, that satisfy z, that da 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 da. And if those constraints that you're putting on it are correct, then you should have a better chance of picking the right function or something close to the right function. So yeah, you can, just because a model is more complex doesn't mean that it's necessarily more accurate, and that is something that you do have to worry about in this space. Yeah. Yes, and this is the modeler's point, right? Because again, when you're building a mathematical model, there are some things that are pretty well established, right? That the rate of recovery is something that just seems to happen at a fixed time. It takes 5 days to recover from this disease, and so you can very simply model that as something linear, right? That is a good assumption. Maybe one of these linearity assumptions is a bad assumption, right? And you just kind of put it in there because you didn't know a better mathematical, when you're building a model, you're always making assumptions. And the point of this is to really look at this and say, what assumptions am I making that are likely to be accurate? Which ones are likely to be completely inaccurate? And if they're completely inaccurate, should I learn a better version of this function that goes there? And that is a very much a modeler's decision, yes. I'll have a very nice slide about that in a little bit. Yeah. Alrighty. So we're all on the same page or slide or computer or whatever. And so if you want more examples of this working in practice, you can go to there. But now I want to kind of say, okay, that's the basic approach, right? That if you have a mathematical model, you can use this kind of approach to be able to augment that mathematical model with machine learning and make better predictions. Cool. What are some other ways to make use of this general idea, right? Just to kind of expand your mind a little bit, because now you're probably thinking like, oh, I have ODEs that have, that I have some terms I didn't know. You can stick it in there. That is a valid use of it. But what if you don't have any equations or what if you don't trust your equations at all? Or are there things that you can do? Turns out that this is this general idea is a fairly, universal kind of approach in some sense. So let me kind of give you another piece here, right? So when you're talking about these pandemics, right, I wrote down a mathematical model, but that mathematical model, let's just say, that mathematical model has a bit of bullshit to it, right? Like, okay, we have the people who are susceptible become infected, but why do they get infected at a linear rate, right? It's okay. People accept that, but we really don't know why a linear rate should work, right? So what do we actually know about a pandemic? Can we write down what we actually know about a pandemic, right? What we really know is we really know structure, right? So what we know is the structure, that people who are susceptible, I guess they could stay blue. So people who are susceptible, they are the ones that become infected, right? Is anyone going to disagree with that? People who are susceptible to disease become infected. Oh, and here's the next thing. People who are infected, they recover. And people who are infected, they could also die. But people who are susceptible to disease, do they die from the disease without ever getting infected? Now that doesn't happen. So this at a high level, this kind of flow is something that we know, that people who are susceptible need to get infected before they recover. So people who are susceptible need to get infected before they die. So if this is all we want to assume, could we encode this amount of information into our process, right? If I want to assume no equation form, but I want to say that I at least know this flow must be correct, can I put this information into the process? And it turns out that using this universal differential equation framework, you can do that. So let me describe this a little bit. Right. So what I can do is I can say, where was the black? Because the black marker was the best one. So I can say, oh, I don't need just one neural network. I can have each neural network is a possible function, right? So I can say, let NNSI be a function of S and I. It spits out a number, right? It spits out some number. And I let NNIR, it's a function of of I and R, and it spits out some number. right? So I can have each neural network. Each neural network is an approximation to some function, right? And if I choose the right weights, it'll be the right function, right? But now I can say I have multiple neural networks. And what can I do with that? Well, I can instead just say, okay, what is the rate of S going to I? It's some function. So let this be SI. What is the rate at which people go from infected to recovered? It is some function. So I'm just going to call this function neural network IR. And there's some function for the rate at which people would go from infected to dead, right? And there you go. This is how if you then take that set of equations where you just say, these are the kinds of things you can be, and these are the rates at which you're changing, then this is exactly this differential equation right here, right? That the change in the number of people who are susceptible is minus the rate of infection. The change in the number of people who are infection is the rate of people who are getting infected minus the rate of people who are recovering minus the rate of people who are dying. And then the rate from here goes to here, the rate from here goes to here. Right? I've made no assumption on any mathematical form. I've just encoded that, if people are susceptible, they can't become dead without first getting infected, right? So, and just from this form of the model, it turns out that there's a lot of nice things that you get, right? Because, so for example, if I make my neural network if I always take the absolute value of it, so all of my rates are positive, that's a simple change, right? Then what you can actually do, if you look at the form of these equations, you can actually prove, without knowing anything about what these functions are, you can prove that in general, S plus I plus R plus D is equal to a constant because of how these rates are set up. So great, you already have conservation of people, but in fact, if you have absolute value rates, then S is always decreasing, and so I is guaranteed to have a peak. You're guaranteed to have one peak in your pandemic for the number of infections. And so this right here is still something that is it's more neural networky than before, right? But it still encodes a lot of the core properties of a pandemic, that the number of people early on will always be decreasing, and that there will be a peak in the number of infections. And if you take this and you test it against other machine learning techniques, you find that this already gives you a lot more prediction from the same amount of data, just because I've already encoded a lot of epidemic properties, right? So this shows you that you don't even need differential equations. You don't even need this prior equation knowledge. You just really need, what really is helping this process is encoding more information about things that you know to be true at a very high level standpoint, right? And you can get really deep with this. So I might lose half the audience on this one. That's totally fine. But okay, so what we're looking at here is we're looking at a case from chemical process engineering. So when you're doing chemical process engineering, you have these giant vats, which are being used to be able to create these chemicals. So for example, when you're creating large numbers of pharmaceuticals, you have these chemical processes, or chemicals that are coming in, they're being acted on, and they have chemicals coming out, right? These are represented through partial differential equations. Now, the interesting thing about this partial differential equation is what we're representing is there is a chemical reactor, and I'm flowing an object through there's a chemical reactor, and I'm flowing a chemical through the chemical reaction, right? And this is what this is representing. So when you're doing this through the vat, I'm basically saying I know the rate at which I'm diffusing the particle, and I know the rate of advection, but what I don't know is what is the chemical reaction, right? And so this is a model that is basically agnostic to what the chemical reaction is. And what I'm saying is, for this thing, now take measurements of what's going on inside the chemical reactor and learn the chemical reaction. And once you've learned the process of the properties of the chemical reaction, then I can understand how to make predictions for the entire space. And so, if you then look at what we get from this type of example, we're able to learn from a small amount of data here. You see, okay, if you think about this as just doing a time series prediction, and you see this line, you might make a prediction that it goes straight or it goes up, yada, yada, yada. But that's not what we're doing here, right? We're taking this data and we're saying, learn the missing pieces of this mathematical model, which is the rate of your chemical reaction. And once you've learned the rate of the chemical reaction, then you can make predictions about what's going to happen in the future. And you can get fairly precise predictions just because the moment that you've learned how a chemical process works, you've learned everything about how that process is going to change in the future. I'm running a little bit behind on time, so I do want to make sure that I kind of catch up a little bit. But so another. Oops. This is, yeah, this is not designed for the high acrobatic formulation that I tend to do here. So one of the other things that you might start to ask is, well, if what's really kind of being captured here is conservation, right? You know, what's going on in machine learning that's an issue is general machine learning is not going to conserve things that you know, right? So if you make machine learning predict, for example, if you make machine learning predict what the temperature of the Earth is going to be, if you try to replace an entire climate model with that, it's going to get a lot of things wrong in terms of it won't have conservation of momentum, it won't have conservation of energy, it won't be able to conserve any quantity, right? So if you want to really kind of take into account all the scientific knowledge that we have, the first thing that you probably want to make use of is our knowledge of conservation laws, right? The energy coming in plus energy coming out has to be equal to, you know, some known quantity, right? Well, that'd be like the energy coming from the sun. So how could you impose all of our ideas of conservation laws through any possible equation? This is one thing that we're submitting really rather soon, which is about you can use the idea of differential algebraic equations for this. So let me highlight this in a nice format. So a lot of people are familiar with ordinary differential equation forms of models. Where did my black marker go? All right, shoes are coming off. It's the mathematician's version of the gloves are coming off. So okay, a lot of people are familiar with u prime equals f of u, right? So this is an ordinary differential equation, also known as an ODE, right? And so all the mathematical models that I've shown so far have been an ODE type of model, right? Now, so for example, let's write down the SIR model. So S prime is equal to minus A times SI. I is equal to A times SI. Minus B times I times R, and then I have R prime is equal to B times I times R, right? So I have a rate at which people go I have a rate at which people who are susceptible become infected, and a rate at which people who are infected become recovered, right? So the thing is here that if I have this kind of model, in this model I have that S plus I plus R is equal to a constant, I actually don't really need to represent this equation right here directly. I could just then say that S plus I plus R is equal to a constant, right? This is an equivalent formulation. The other form of the equations guarantees this conservation law to be there, but what if I didn't know all the equations? It might be good to just say, I know that this conservation law exists, and try to find out what equations are true, given that I need to have this assumption, right? So how can I make this happen? It turns out that there's a small trick that makes this really nice. So if you allow for there to be a mass matrix over here, M, you're able to incorporate all types of these conservation laws into your dynamics. So how would you do that? Let me actually just write this down. So I have, I have M over here, and I have my vector U, which is S prime, and I prime, or S prime, I prime, and R prime. And then equals this set of differential equations over here, minus ASI, minus BIR. And then this can be, this would be S plus I plus R minus N. Right? Can anyone see how to choose a matrix M such that I represent not a system of equations that all are ODEs, but also has some equations that are conservation laws? Well, for me to get this equation up here, I need that S prime, so this M times S prime has to be equal to S prime, so this should be 1, 0, 0. And now for this one, I need to get, M times I prime is equal to that, so I'm going to get 0, 1, 0. Right? But if I want to get this conservation law, well, this conservation law doesn't have any of the differential variables. So I just make this be 0, 0, 0. It turns out that this formulation of a mathematical model can incorporate models that have conservation laws by using a singular matrix for M. So this is known as the mass matrix formulation of a differential algebraic equation. But if you use this, then that means all the ideas that we had before of, oh, I want to encode that, I have this property of my ODEs, I have some prior scientific knowledge. But now if you have conservation laws that you know, then you can directly impose those conservation laws. And if you write it inside of this form, mu prime equals f of u, and if you can solve these types of equations directly, then you can actually impose prior known conservation laws and prior known physics, and just learn the parts of the equation that you didn't know with respect to any possible conservation law in those equations. Yeah? Yeah, yeah. Well, so you get 0, 0, 0 equals s plus I plus r minus n, which is that equation. Right, so you can actually also mix that, s prime plus s, so you can get mixtures of these. It just turns out that conservation laws are just areas where the mass matrix has a 0 row. So that's why you get a guarantee that if you have a conservation law, then your mass matrix is singular. But as long as you have ODE solvers that are able to deal with singular mass matrices, then you're able to handle these. Then you're able to represent these types of equations. You add neural networks to this side, and suddenly you have neural network forms that can be written with arbitrary conservation equations. So that's neat, right? Because now if you know something needs to be conserved throughout your model, the number of people or energy needs to be conserved or angular momentum needs to be conserved, you can basically just say, hey, here's a general representation where I can impose the conservation laws that I want and learn any possible model that satisfies the conservation laws that I know need to be satisfied. Yeah, yeah. Oh, yeah, so well, yeah, so if you add another line, then you actually have an over predicted system, right? My point here is that if you have the ODE here, right, that is r prime is equal to b times I times r, right? If you look at your rate equations for this kind of equation, this set of ODEs, s equals s prime equals minus a times si, right? This rate having the exact opposite being here means that anything that's moved from s moves into I, and anything that's moved out of I moves into r. And so from this ODE, you can actually sit down, and these three ODEs, you can prove that there exists a conservation that s plus I plus r is always equal to its initial conditions, summation, right? So if you had the ODEs, you can predict this. But if you're trying to now start to learn the equations, what you really want to do is you want to impose that this property exists and learn something about, learn for me all possible infection functions, but whatever infection function you choose, please make it so that way I have the conservation law imposed, right? And in order to do this, what we can do is you can rewrite our equations into this differential algebraic equation form where we fix the mass matrix, we fix here, and now we can say move one of these equations around, and we can learn equations in here, and we're guaranteed that no matter what equation we choose, we always have our conservation law satisfied, right? This is another way of allowing neural networks to have their, I'm all possible functions, but still impose whatever relationship we want to be imposing. Yeah. Yeah, I mean, you can also impose that the sum of those are 0. Yeah, I mean, then this gets into the numerics of differential algebraic equations about which one is going to be more numerically stable and all that. So that'll be a big topic. But I mean, what I really just want to show here is that generally, if you use differential algebraic equations, then generally you can have things that have differential variables and things that don't have differential variables. And these full sets of equations can be used to be able to impose any conservations that you need. And you can always represent them as just ODEs with mass matrices, right? And so yeah, you can then do s prime plus I prime plus r prime is equal to 0. You can do that by just making this 1, 1, 1, 0, right? And so yeah, there are many different ways that once you're in the differential algebraic equation form, you have a lot more flexibility in terms of imposing all sorts of conservations. Yeah. Well, I mean, if you're going to use positivity, then that will no longer just be a straight differential algebraic equation. That'd be a differential inclusion, which is probably the next paper that the student's going to be working on. So you have to then be able to come up with ways that you do training with respect to differential inclusion and solving them. But yeah, you can start to understand, once you see this, then you can come up with other equation forms where you're like, oh, it'd be really nice if you can impose all these properties and these properties and these properties. And then that's really the science that's going on in the scientific machine learning field. That's why I want to go through this topic, right? That yeah, you could do this on ODEs and it gets you some nice pieces, but really where a lot of this is now going is being able to encode all of the information that you have, that S prime has to be positive and yada yada yada. And once you encode all that information, you put a small neural network in, and you show that the more information that you're able to encode in the model formulation, the less data you need for that to be predictive. Yeah, and so there's a lot of extra formulations using complementarity, yada, 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 to be able to encode inequalities and all these other properties as well. Alrighty, any other questions in there? All right, so I'm kind of going through this somewhat nonlinearly. That's great because I, as everyone else, are a neural network as well. So one of the questions that actually came up here as well is, can we start to include probabilistic information in this as well, right? Because this seems everything I've done here sounds very deterministic. You give me a mathematical model and some data, and I will tell you what mathematical function you are missing. And round of applause, we now have automated science, right? But we all know that science is not that easy, right? You need to have some sense of uncertainty if you're with any scientific measurement. Well, that means that you're going to have some uncertainty with respect to the types of scientific models that you're learning from the data. So what do you do about that? So what you could begin to do is, if you look into, for example, this paper that we had on Bayesian neural ordinary differential equations, what you can do is, instead of doing this process where you learn the weights, you can use a Bayesian process to come up with a posterior distribution for the weights of the neural network, right? And so this is a kind of a standard thing to do, Bayesian neural networks. And so what you get is you get a probability distribution over the possible neural networks, right? But remember, here a neural network is what we're really doing with the neural networks is it's a function approximator, right? So if you do a Bayesian learning process on the neural network that's embedded within your scientific model, what you're really saying is, I have learned a probability distribution over missing functions that can represent the missing part of my model, right? And what we're able to do here is we're able to show that that can be a useful quantity. So here's the same Lockable-Terra equation kind of setup that I showed before. Right, the very, very first examples all the way back. Let me So on this exact example where I say, oh, I know these quantities and I'm going to learn some other ones. And now I'm saying, instead of directly learning the neural network, use a Bayesian learning process for the neural network. So I learn a probability distribution over the missing quantities, right? So I now have a probability distribution over the missing functions. And what can I do with that? Remember what I did with this function is I said, well, after I've learned the neural network, I can turn it into actual terms, right? So can we do this in a Bayesian way as well? What we can do is we can get a probability distribution over the weights of the neural network here, which gives you an induced probability distribution over the possible functions that are missing from my model. And what I can do is I can sample, here's one neural network, here's a second neural network. These are all possible representations of the missing function, and I could run this process of sparse identification on that missing part of the model. And you get a really interesting result when you do that. What you're able to do is you're able to see that, for example, in some of the cases you have very complex functions, but in many of the cases you just have a very simple function. In fact, more than 70% of the time, you only get that this quadratic term is the piece that's missing, which is actually, in this case, we know from the generated data that this is truly the thing that's missing, just this quadratic term. So you're able to turn this from a problem of, hey, predict for me the part of the model that is missing to, tell me what terms are potentially missing and give me a probability distribution over what functions I should be adding to my model. With a high probability being the ones that you really believe that you need to be adding to the model, and the low probability being the ones that don't necessarily help the fit all that much, right? And we're then able to take this to much more extreme cases. I don't want to go into the full details here, but in a case with a partial differential equation, so we're doing this now on for example, the Fisher KPP equations, where we're then saying, okay, we're trying to learn what the diffusion equation is with respect to the Fisher KPP. We're able to find that, for example, in 73% of the cases, a quadratic function it works well for the missing term, and in 27% of the cases, a cubic function works well for the missing term. In this case, we actually generated the data with a quadratic function, and so it's giving you a nice form of uncertainty to represent this is most likely the model that is missing from your data, right? And so hopefully this is kind of answering the question from earlier. Are you able to take these kinds of cases and be able to bring this to the probabilistic space? You need to read the paper in a lot more detail in order to kind of see how the processes of all this. But essentially, you replace everything where I said, train the neural network and find the weights with instead do a Bayesian procedure for finding a posterior, and then you can sample this function and do all this kind of model discovery elements in a way that is now giving you uncertainties with respect to the models that are being spit out. Of course, your computational cost grows by like 100 times when you do this, but it is a potentially possible process, right? So now I want to kind of get to this is the academic hat of here's all the things that we've been doing, and here's how scientific machine learning and its methods are growing. I want to kind of talk about a few stories now about how this is getting industry adoption to be able to demonstrate, how you can think about using this as a tool. Because again, machine learning is a hammer. And part of using this hammer correctly is understanding how to use it, right? So all of these things about, you can use it to improve this model and such. I'm going to even say that even all of that is academic. It's great that you can improve a model, but if you're in the real world and you don't know what your true model is, the neural network spits out a model for you. How can you actually use that, right? So let me tell you instead, I'm going to tell you how to use this kind of tooling by talking about a story, right? So one of my other hats is coming on here. Remember, I'm also a director of pharmacometrics at one of my startups, Pumas AI. And one of the things, and what we really work on at Pumas AI is this problem of individualized patient predictions, right? So if you are someone who is in the pharmacometrics field, this is how we display it. But I feel like this doesn't really do it justice. I believe that the easiest way to understand what's going on in pharmacometrics is actually to look at it from the mathematical modeling standpoint. So what do clinical pharmacology models actually look like? Here's what they look like. So what you do is you say, okay, when someone first walks into a clinic, I can measure a few things about you. I can measure your weight, I can measure your height, I can measure some properties of your blood, right? All of these things are measurable quantities. And when you do that, when you do walk to your doctor, they do give you this information. They do take this information from you, right? So this is what's known as covariates, right? So what you do is you start with these covariates. You say, I know something is different about this patient by this covariate information. And now what I want to do is I want to be able to take this covariate information and I put it in what's known as the structural model. Right? So the structural model takes, for example, the weight and your sex, and it prints out these different coefficients, Ka, Cl, and V. And what I do from this is I then say, I put these as parameters into a differential equation, and what this differential equation is the chemical concentration of the drug within the central department of your body and other parts of your body. Right? So this is then a model of the amount of the chemical concentration in your body. And the reason for this is that you want to be able to say, you want to be able to, from the clinical trial, be able to show, for example, that 50 milligrams per liter might be the optimal amount of drug in your body, and if it ever goes over 100, then it might be toxic, right? So now you have a model that is how the drug is changing in your body over time, how it decays, how it leaves your body, but it is dependent on the weight of the individual and the sex of the individual. And the whole goal of clinical pharmacology is to learn how different people will react to your drug, to be able to find out, A, what is the proper dose I should be giving people, and also, B, are there different dosing populations, right? Do I need to be giving males versus females? Do they need to have different dosage levels? Do I need to have dosage levels that are dependent on weight? Or can I just assume that this, everyone is reacts similarly enough to this drug that is safe to give everyone the same version, right? This is the general goal of clinical pharmacology, to answer that question about optimal dosing using this process of finding an internal drug model for how it is being released from your body, which is dependent on that covariant information, right? So this is the central problem of clinical pharmacology. How do I learn how different people will react to my drug differently? And so what I did for many, many, many years is I worked on, if you know some of the work that I've done, I worked on making ODE solvers really fast and be able to do inverse problems to find the parameters of this model in a way that is really, really, really fast. And we got a very front, we got a front row seat on the utility of this kind of modeling, because in 2020, actually Moderna partnered with us with Pumas AI to make it be the go-to tool for the way that they would put together their clinical trials and their clinical analysis for the Moderna COVID-19 vaccine, right? In fact, this is a quote from Hussein, who is the director of clinical pharmacology at Moderna, who said, "Pumas emerged as our go-to tool for most of the analyses in the recent months," right? And this was in 2020 when they were working on their novel vaccine, and it was one of the fastest vaccines to ever be released using Julia as one of these core tools, right? And we were so excited about the fact that, oh, hey, we were able to make this process so much faster. And when we started to do the retrospective on, oh, hey, how could we make this even faster? Right? We always think, how do I make my code faster? How do I make my fitting process faster? How do I do this faster? And can anyone guess what most of the time was spent doing? Not just the engineering. What, for this whole process of coming up, we build a model, we fit it, we find all this process. What was most of the time in this process? What do you think was being spent on? Finding out what functions you put here, right? Okay, you have to run the fitting process. The fitting process takes 2 weeks on large data sets, yada yada yada. But actually coming up with the functions to put in your model, people were trying different things, trying to read the scientific literature, being like, oh, I heard that if you use this capsule design, then it seems to have a weight-dependent procedure. So now let's go to the lab and try that. Oh, actually, our capsules actually it isn't related to that one. Right? So coming up with these functions end up being 90% of the time, and then the 10% of the time that was a compute, we did that really, really, really fast. But most of the time, when in this real world, it's actually just trying to come up with a model. And you've probably seen this before, right? You're either a graduate student who's building a model, or you are an advisor, and you're like, why is this model taking forever? I just want you to make this plot. And you spent the last 9 months debugging your code to find out what functions go in here, right? It turns out that most of the scientific process is coming up with the model. And do we have a way to be able to help come up with models? We do have a way to be able to help come up with models, right? Now, if I was to go to the FDA and say, hey, look, whether someone for weight and your sex, whether they should be able to use this pill, put their weight and sex into this neural network and spit it out, and we can make a prediction. Like if I was to go to the FDA and tell them to put that on the pill bottle, they would say I'm insane, right? But what I can do with this is I can say, hey, I can use neural networks to be able to find the predictive process, and what do I do with that? Well, when I use the neural networks to find a predictive process, I can write down everything that I know about the process, and the things I don't know I can cover with neural networks. And then what I can do is I can have it spit out, hey, look, these are the functions that I believe are missing, right? And when I spit out the function that I believe are missing, it goes, and someone will look at that and go, oh, you know what? Weight should be, the clearance of the drug should be dependent on weight, or the clearance of the drug should be dependent on the metabolism rate. We didn't think about that in our original version of the mathematical model, but this makes sense. Now let's go look for the literature justification of that term, right? And so instead it started to become a tool for helping modelers get quicker to the model, right? It basically turned the process of, I don't know what I'm missing, let's throw a bunch of things in the model till we see what works, into something that says, hey, here are 4 potential things that we think you are missing from the model. Go look for literature justification. If you do actually find a justification for that model piece, great, you just found out what goes in there. Now we have a better model. And so it really it has turned into something where it keeps the scientist in the loop. The scientist is still doing a good procedure, but what you're able to do with this kind of process is you instead start by writing down the mathematical model that you know. you let the neural network learn, you have it predict out what missing terms there are there, and then you look at the missing terms and you say, what could these missing terms be? I know a lot about my system, but why would it say that there's a term that's, weight times sex divided by this is changing the gut volume? Well, maybe that could be this scientific procedure. And you look in the scientific literature, and boom, you find a hit that the lipid capsules are the degradation of lipid capsules in the stomach ends up being dependent on some sex-dependent protein, right? And you go, got it, I got my hit, and now I have a justification for this term. And this gives you a quicker way to be able to find, and build out these more complex versions of the model. And so I think that, I showed this at first as like, oh, hey, this is really making science automatic. I wouldn't think about it as really an process of automating science. It's more of a process by which scientists are now being helped by saying, oh, here's most of the model. Here's things that you could potentially add to your model that would improve the prediction power of the model the quickest. Which of these makes sense? Now go justify that. Once you've justified it, now you can add that to the model. I think that this kind of example has been a very nice one because it's become real world. And now in 2024, if you actually, or 2025, wow, we are really storming forward in this world. And now in 2025, you can, if you go to the Pumas AI website, you'll see that we're running a bunch of workshops on something called Deep Pumas, and a lot of recent clinical trials are using Deep Pumas. That is just this scientific machine learning put into an actionable form for clinical pharmacology, and so that is like this real use case of it. And now let me see where I'm at. Yeah, so let me just kind of end by telling a little bit of a story. Now to be able to say, okay, we want to really democratize then all of the scientific machine learning, right? Because now that we've really found that this is a nice hammer to be able to use in a lot of use cases to at least augment science. What we are then trying to do throughout the rest of the Julia ecosystem, and especially with Julia Hub, is make it so that way all the different ways that people throughout different industry practices are able to actually adopt this as a core tool, right? So now, one of the things that you actually find when you go to a lot of people who are doing modeling is, I know that a lot of people in the academic space, you're either writing a model from scratch or you're inheriting a Fortran code from 1970 that your advisor's advisor's advisor wrote, right? But it turns out that, in a lot of industry cases, there's another way that we've gone around this problem. How do you build models? And it's through composable modeling frameworks, right? So you might have heard the term Simulink before, or Modelica, or if you're in chemical process engineering, GPROMs, right? These are a lot of these industrial tools, and what they allow you to do is be able to write down, like, I have a model for how a resistor works. I have a model for how a capacitor works. And then you just say, I connect all these models, and it will generate a composed version of the model, right? And so currently, if you look at the way that automobiles are built, or you look at the way that airplanes are built, they're all built using some of these composable modeling frameworks where people in different departments can write down, here's a model of a wheel, here's a model of a wing, and then compose them all into this giant version of the model, right? So if this is the way that people are actually building models today, then what we need to do in order to bring that into the scientific machine learning world is we need to build a modeling framework that is built on this composable modeling idea, but incorporate the ability to do all of the scientific machine learning work. And that's really what we've been spending a lot of our time to be able to do, to be able to grow the influence and the usage of scientific machine learning. And what this looks like in practice now we get to more composed figures that are starting to look, a lot more professional, because now we're kind of jumping into that domain. What we're able to do is we're able to say, we can build a graphical user interface where someone can put together their model, right? They can have someone build a model of a wheel, someone build a model of the drive shaft, a model of the engine, and piece this all together. But when you piece all this together, there's going to be someone that just says, yeah, we really don't know how our electrical engines work. And you go, well, okay, if we don't know how that one block in the model works, well, what about turning that block in the model into something that's augmented with a neural network, right? And retrain and use the data that we have to then train this neural network to improve that one part of the model, which then improves our whole digital twin, right? Now this is really kind of taking that process I described before, all down in equations, and now turning it in something to where people who are now just composing together models at a high level using graphical user interfaces can use the same idea, right? It's just neural networks are compensating for functions that we don't know. We piece them in there, and we learn real functions that are better predictions of how cars will drive autonomously, how airplanes will take off and land. We learn better versions of this by finding out which components within our model are the ones that have the least accuracy, and making them be better accuracy by adding the physics we didn't know, extra friction terms we didn't handle, extra things to do with wind drag, and all these extra features by learning those directly from the data if we have not physically predicted it before. And this is what we then are doing with something called JuliaSim. So this is like, if you've been wondering what is Julia Hub actually doing, and what is the day job behind the people of the SIMO kind of work, this is what we've actually been doing. We've been building this graphical user interface that pulls together all of the tooling that I described before, automates it with a few button clicks, and makes it so that way you can do all of this kind of scientific machine learning in a way that where you can use pre-built models of industrial pieces to be able to build real-world objects, like, for example, a real-world air conditioning machine. And then when you check that, oh, here, it has all the properties of, I'm using refrigerant R32, it has two-phase flows, all these mathematical details are captured, but we will always miss something. We will always miss some level of mathematical detail, and so we can instead use the scientific machine learning approach that we described in order to learn the missing physics, predict the functions that we didn't know, further improve the model, and you do this as a process that's just continually improving a library of models that we're then able to share with company A, company B, company C, and continually just improve the way that we and predict how the AC is able to work on an airplane versus how the AC works inside of a car and how it works in your home, until we just get better and better models, and that are just much more closer to reality. And the closer we get to the reality, then the closer we're able to, or the better we're able to then improve the control techniques, the predictions for the amount of battery usage, and all the properties that's associated with this. I kind of want to just end with a bit here where, are we actually doing scientific machine learning in industrial cases? Yes. This is actually a really nice case where we worked with the Williams racing team, which is one of these Formula One teams. In fact, a lot of this was done by us. So I'm just taking the credit, but actually this is mostly his slide here. Where basically what we're able to do is we're able to say, okay, in the first case, so what we're actually going to be looking at here is the results from the speed over ground sensor. So when you drive this Formula One car, what we want to do is we want to be able to predict, using a sensor that is pointing down on the ground, what is the current angle of the car, right? So we want to be able to predict the current angle of the car as it's driving around a turn. Now, why do you want to have an accurate prediction of that? Well, the reason why you want to have an accurate prediction about that is because there's an optimal angle of approach for every single turn that is predicted from the race computer, right? So, people who are all these, all the nerds, part of the F1 race, right? They're all making predictions like, oh, at this turn, so at this turn, like, let me just kind of draw like a little racetrack, right? So let's say you have a racetrack like this, right? They go, oh, the best way to do this turn is to maybe take this inside line right here, right? And you go, oh, this is the optimal angle of approach. So you have an entire team of people helping the Formula One racer find out what is the optimal way to drive every single track, right? Now, when they actually go onto the real track, what you want to do is, they have the headphones. You might have seen those, and they have someone talking to them during the race. They're basically trying to tell them, like, oh, hey, this is the optimal angle of approach, but we notice that you keep on taking it at slightly too wide of an angle. That is slowing you down. You keep on doing this one wrong. Take it at a tighter angle next time, right? This is the type of information, if you ever watch one of these Formula One races, you'll hear that this is the feed that is being sent to the driver, right? But in order to actually send that feed to the driver, they need to actually know what is the angle of attack that they're actually doing on the field. And the way that they get that information about the angle of attack is through a sensor, the speed over ground sensor. And now I'm going to show you a picture here. On the right, now just look at the one on the right for now, right? On the right, what we have is their original prediction, right? So here is the true angle of the car. The yellow underneath it is a true angle of the car. And then the car that we're showing on top of it is the prediction of the angle of the attack from the speed over ground sensor at a given point. And if you're watching this, you should be able to go, well, wouldn't it be very hard for you to be able to tell the driver, like, hey, you're taking this at 45 degrees, the optimal is 42 degrees, right? With this kind of information about the angle of attack, it's very difficult to be able to tell the driver pretty much anything. And this is one of the issues that the Williams racing team was running into. They're not getting good signals from the actual race. And the reason here, though, is that the technique that they were doing is they said, well, hey, look, this is data. I know that machine learning does data, so let me get data of this speed over ground sensor going over the track, and let me just predict. If the data sees this, then here is the angle of attack, right? Just a pure data learning problem, right? And what you can see is that it just didn't do very well. In fact, it's very non-physical, right? The car cannot actually jump around like this. That is not something that a car could even possibly do. But machine learning can predict that the angle of attack is 30 degrees, and the angle is 45 degrees. It could just make a new prediction each time. And so the issue that they're running into is like, hey, we can't really relay to our driver good information because our real-time predictions of the angle of attack are completely inaccurate. So can we instead improve this, right? And so, not going into too many details here, but basically we can come up with a version that, although simple, incorporates a lot of possibilities of what a vehicle dynamics model can do, and start to say, okay, position is the integral of velocity, velocity is the integral of acceleration. These things have to be true, and certain properties have to be true. If we just incorporate this kind of information, the car can't jump around because that's completely unphysical. That would require a huge angular momentum. So what happens if we put a simple physical model into this process is we get what's on the left here, right? Again, the same amount of data, the same data, of the speed over ground sensor. But what we're able to do is we get a much better prediction for how the car's angle of attack would be given the speed over ground data, because it is not just machine learning, it's machine learning that's augmented with a simple form of vehicle dynamics. And so this is the kind of results where you can start to say, well, we can really make use of this in not just some academic scenarios, but we can make use of this in the way that we're interacting with putting sensors on real vehicles. And these are not just machine learning problems, right? You can always think about this as, oh, if I get 1 billion more data points, then I can make it better, right? But this is a way to kind of go, I know something about science. I know how cars work. I know how Newtonian physics works. Let me incorporate a little bit of that, and now I don't need 1 billion data points. I can instead make a much better prediction with the same amount of data, right? And just to show you how cool scientific machine learning is, I don't know if you know George Russell, the current number 6 driver in Formula One, right? Because of this project and everything, I got to go there and got to go clubbing with them and meet him. So the end result here, I know that there's a lot of students in here. You might think that, oh, this is super nerdy talking about all these equations, but no. Math is cool, right? We got our logo on a Formula One car with good math, so you can do that too. So I just want to throw that in there as a fun little bit to basically say, hey, look, we are really bringing everything that I described here. It just sounds so abstract. It sounds like it's really in the weeds, but this is really the future of how every device is being created, and industry's really taking notice, right? Really what we're looking at as a future and what we're really building out right now is this kind of idea that, if we know something about physics, so we can start by writing down all the physical laws that we have, right? So think about on a car, right? You have a car or an airplane, and you write down everything that we know about how the car works and the airplane works, but as you're driving, you're getting more data. And as we get more data, we can stream that data back to these neural networks. And these neural networks are then making predictions. Oh, here's something here's a better prediction of how the wheel physics works. Here's how the wheels slide. Here's how the friction works. And we're just continually improving the types of models that we have. And this is then giving us automatically improved models, so that way someone who's building the next version of the car, they can then pull in a version of the equations that already has these improved physics as part of it. They can look at what did the improved physics automatically learn from the data, and how should I now be changing the control system? How should I change the wheel size? How should I change the way I'm designing the braking system based off of this improved model? And now what we're doing is we're building out this entire kind of software ecosystem, so that way you can build these models and have this automated training process just all work in tandem. And then we're partnering with groups like Boeing and other car companies and such to be able to make this be the way that we're basically doing all physical modeling and outputting all devices, right? If you think about it, your next car is not something that will be static. Most people here, the next car that you buy is something that will be that will have, you know, things like lane assist and things like the automated driving and all this. And every single time you get an over-the-air update, the over-the-air update needs to be able to, it actually is a model of the car. It has a model of the car that's inside of it that is then telling it, oh, here's how the car moves, and here's how I'm interacting with people in the environment. And that model of the car is actually improving almost on its own, iteratively, iteratively, iteratively. And that's how we're getting to this next generation of devices. And so hopefully this gives you an insight, you know, from the very bottom of how the equations and the neural networks work, all the way to the very top of now the next time that you click, you know, upgrade, you know, you not just upgrade my phone, now you're going to be clicking buttons like upgrade my car. And the way that it's able to do the lane assist automatically has now learned a better friction model through these scientific machine learning approaches, which then helps it drive a lot nicer. And this is how this whole stack is looking out. So, you know, I do have a whole nother section in here, which is all the mathematics, yada, 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 for how the training process works. But I thought, you know, I thought that this version of the talk might be a bit more good for the majority of the audience. And I think that I'm about at time now, right? Yeah, so 11:57, so I won't even go to the next part. If you happen to want to have all the mathematics for how the training process works, well, I'll be giving a 1-week workshop in Norway. I'll also be doing that in Sandals. If you're really curious about how that will turn out, that is 2 weeks from now, and I can chat with you if you want to join it. So thank you very much, and I'll take some final questions. Alrighty, there was a billion questions during that. Is there a billion and one? Alrighty, then that means it's time for lunch. Thank you, y'all. I do want to say one thing, which is that reminder that there is karaoke on Thursday. It is mandatory. You will not get your reimbursements without going to karaoke. Yeah, yeah. Now to Joao.
Thanks, Chris. Thank you, fantastic lecture. Thank you very much. So if you're online, that's it for today. Thank you for joining us once again. I will be back again tomorrow at 9 a.m. local time here, of course. For those who are here, let's go down. So we have lunch now, of course, 12 to 1. But if you don't mind going down to the garden, let's take the group photo because the weather seems fine. Let's take advantage of that. And then we come back for lunch. So if you go down to the first floor in the garden, through that central part, then turn right, you'll see the group forming there. Anything else? Okay, so see you tomorrow if you're online, and have a nice lunch.